All right, welcome to Module 2, Lesson number 2 in SISAS. We're going to talk about how Cisco Identity Services Engine works with the public key infrastructure. Very, very important concept. There's a lot of functionality that relies on the use of this public key infrastructure. We'll talk about how we do server authentication in EAP and certain types of the extensible authentication protocol. We do require that the server identifies and authenticates itself based on public key infrastructure and certificates. We'll talk about the TLS protection and how transport layer security provides protection for communication in our ISE environment. We'll take a look at the X.509v3 certificate, what's included in that, what kind of information is necessary to have in that certificate to be able to identify the ISE platform. We'll take a look at the server certificate itself. How do we validate the ISE certificate? How do we validate the ISE signature? And then the procedure for enrolling ISE within the PKI environment. How to import the CA root certificate into the ISE certificate store. How to generate a certificate signing request if we want to go ahead and have a digital certificate signed by a CA or a third party. How do we bind the returned certificate to the pending CSR? Meaning that once we've submitted our CSR and the certificate gets signed, how do we then go back and bind that to the actual certificate? And then finally, how do we enroll, verify that the ISE platform's actually been enrolled in the PKI, with the PKI infrastructure and certificate process? We know that the Cisco ISE platform relies on what we call the public key infrastructure to provide secure communication. But what is that secure communication used for? Well, clearly it's used for HTTPS communication between, say, your client browser and the management server in the environment. But also it's used for client and server authentication if you're doing some sort of transport layer security related extensible authentication protocol process, right? We talked a lot about 802.1x and how various EAP processes work within ISE, and we'll get into some more of that in additional detail a little bit later on. There is a web interface, and we'll see this throughout this lesson, that allows us to manage these PKI credentials. Fundamentally, there are two types of credentials that we'll talk about. There's something called a local certificate, which is basically just used to identify the Cisco ISE server to other entities like EAP supplicants, external policy servers, or management clients, and so on. These are called identity certificates. And then we have the local certificate, but we also have something called the private key, which is stored in Cisco ISE to provide its actual authenticity. Cisco ISE identifies when the local certificate is about to expire. It provides you warnings, and in the audit logs you can identify when that certificate's going to expire. There's a message that indicates that the certificate is expiring in less than 90 days, and then there's another message that indicates that the certificate is already expired. The other type of certificate that we have is what we call a CA certificate. And we're looking at basically the architecture here in this particular diagram. The purpose of this particular certificate is it's used to verify remote certificates that are presented to Cisco ISE as well. Certificate authority certificates have a signature in them. So it's kind of a trust certificate that allows us to identify if the supplicant is providing a certificate to the ISE platform. We can then verify the digital signature of that certificate based on a root certificate or a CA certificate that's been installed on the ISE platform. All right, and we'll talk about the different processes here and what's the difference between a local certificate, what is the certificate signing request, and then how do we also manage the certificate authority certificates as well. So we're going to talk about a lot of these different areas, but let's go ahead and start off by just taking a look at the server authentication in the extensible authentication process. So let's say, for example, like I said, we had essentially two different certificates. We have an ISE certificate, which could be locally signed or it could be signed by a certificate authority. So there's a CSR process, certificate signing request process, that allows us to send in a public certificate so that the CA can then verify the identity of the ISE platform, the company that's managing this platform, and then they can put their signature on that certificate and send it back down to the ISE platform as a digitally signed certificate. And then we also have the CA root certificates, or what we call the certificate authority certificates. These are the credentials that are used to verify certificates that are presented to ISE, like I said. We'll talk about the whole concept of OCSP, the Online Certificate Status Protocol, and certificate revocation lists, and how we can manage if the supplicant somehow is providing a certificate to ISE. We can use these CA root certificates to be able to identify the validity of those certs that were issued by the supplicant itself. Okay, Cisco ISE does act as an EAP server in a lot of different deployments. So it is going to require certificates that can be validated by the clients. So when we install our ISE platform in the network, there are a bunch of pre-installed certificates that come by default, but they're not verified by the client supplicants. They can't be verified because they're self-signed, I guess you should say. They're not signed by a third party. To allow successful certificate validation, we need to make sure that those certificates get signed by a certificate authority, which means that we're going to have to issue a certificate signing request to the CA. The CA is then going to grant access or grant a requested certificate with the digital signature, and then we install that on ISE, and that's what we present to the clients if we need to authenticate the ISE platform to our clients. The supplicant then can validate the ISE certificate by having its own CA certificate installed, which is usually installed in the browser or some other, some other method locally on the machine. Okay. With regard to how TLS or TLS protected communication works, there's a couple of different components to transport layer security. Number one, we want to be able to verify the authenticity of an endpoint. All right. Number two, we want to be able to provide confidentiality and integrity for the communication channel. The way it basically works is just about the same as any other TLS process. You've got some device that wants to connect. It's not going to let me draw in here. There we go. All right. I guess we're not going to do it that way. All right. We have some device that wants to connect to our server. When this device sends in an HTTP request, the ISE platform is going to send over its publicly signed or digitally signed public certificate to the supplicant. So our public certificate goes over to the supplicant. Now, that allows us to identify the authenticity of the ISE platform because I can use that CA certificate to verify the signature on this public certificate. But there's a second part to this TLS process, which is encrypted communication. Being able to provide the ability to communicate over an encrypted channel using most likely something like AES. Well, the problem with an AES process is that it's a symmetric encryption process, which means that both sides of that channel need to have a key that they agree upon for that encrypted channel. All right, well, that's not a key that we statically configure. It's a temporal key that gets dynamically generated during the process. So how can I ensure that this key and this key are shared between the two endpoints without actually compromising the key by sending the key over some sort of public channel and not having the overhead of trying to manage that key distribution through some sort of out-of-band key distribution method? So we take the public certificate of the ISE server and we encrypt that key with that public certificate. And then we send that over to the ISE platform. The ISE platform then can decrypt that key with its corresponding private certificate, which nobody knows except for the ISE platform. So this provides us the ability to establish that encrypted channel between the two endpoints so that we can have private communication and so on. And it's the same way that it basically works with just about any type of TLS or SSL type of environment. Make sense? All right. Now, one of the things that we talk about is a digital certificate, and that digital certificate comes in the form of an X.509 certificate. X.509 is basically a standard format for defining the format itself of something called a public key certificate. They're used for things like TLS, SSL if you're using HTTPS, for browsing the web, or they're used for electronic signatures, digital signatures, and so on. An X.509 certificate contains a public key and the identity, usually based on the host name, the organization, an individual, and it's either signed by a certificate authority or it can be self-signed, meaning signed by a certificate authority about as a third party verifying the identity of whoever the certificate is being issued to. Sometimes we can work with self-signed certificates, but in the case of network communication, being able to communicate across the network in a secure manner, we typically like to have these certificates signed by a third party. When a certificate is signed by a trusted CA, that CA has gone through a process of validating the identity of the individual that holds that certificate. So through that relationship, the supplicant's trust of the CA and the CA's verification of the identity that's providing the certificate, we've created this kind of circle of trust between the individuals. All right, so all of the documents, the X.509 certificate itself is actually digitally signed using the private key of the certificate authority or the signer. Right. Besides the format of the certificate itself, X.509 as a protocol also specifies certificate revocation processes, which provide us a way of distributing information about a certificate that may no longer be valid. There's also a certificate path validation algorithm, which allows a certificate to be signed by an intermediate CA, which would then be signed by other certificates, eventually getting to that core trust anchor that we're looking for in the relationship. This is an ITU standard based on ASN.1 and ITUT, and there's several components in the certificate. You can see a lot of the components listed here. ASN is what we call the abstract syntax notation. In this particular case, we're looking at an X.509v3 digital certificate, which has a version number, a serial number, a signature algorithm ID, which allows us to identify how it was digitally signed, an issuer name, the validity period, not before, as well as not after, subject name, subject public key information, including the public key algorithm that we're using and the public key itself. And then optionally, we can have things like issuer unique identifier or subject unique identifier extensions and so on. All right. Each extension has its own ID. These are called object identifiers. You can kind of see it listed here. We don't see the object identifier here, but it can also be part of the certificate as well. And we don't necessarily have to get into the details of certificates and cross certification and the root certification authority and different levels. But what you're seeing here is just a sample X.509 certificate. It was signed, it was issued to hq.srv-ca.securex.local, valid from November 18, 2013 to November 18, 2014. It's a RSA 2048-bit key. RSA stands for Rivest, Shamir, and Edelman, which were the three gentlemen that actually came up with this concept of public key cryptography. Yeah, that's pretty much it. All right. Now, when it comes to the use of the certificate, this public key or certificate is actually a very critical component in identifying the transaction or the communication that occurs between the two entities. We can send private messages to the subject by encrypting the data with the public key of the subject, but only the entity that has the corresponding private key would be able to then decrypt that information. There's a couple of different ways we can use these certificates, right? We can use them to provide non-repudiation of origin, digital signing, etc., where we would sign with our private certificate and then somebody could verify that signature with our corresponding public certificate, or it could be in the used in the case of cryptography, where we're trying to provide confidentiality and integrity. And in that case, the data is going to be encrypted with the receiver's public key, and then the receiver's private key is used to decrypt the information. It really just depends on what your overall objective is. All right. For example, and they list this example in the book, but a simplified description of the TLS session is as follows. Number one, the client initiates a connection to the TLS server. The server presents its certificate to the client. That would be the public certificate, not the private certificate. The client then validates the signature on the certificate, which is essentially a hash using the private key of the CA or the root. And then the client generates a session key, which is used for that shared secret key for encryption. The client uses that public key of the server, which was part of that certificate that it received, to encrypt the session key. The client then sends the encrypted session key back to the server, which then can be decrypted with the private key. And then now we have our bulk encryption key. That was the diagram that I was kind of drawing, or made an attempt to draw on the previous slide, where we had this exchange of public key and then session key and then private key to decrypt and so on. All right. For most EAP methods, ISE needs to have some sort of identity certificate that the clients will be able to verify. For example, in PEEP and GTC, EAP GTC, the clients verify the server certificate, and then the server authenticates the clients using some other credentialed method. In EAP TLS and PEEP TLS, each side verifies each other using certificates. That is one of the things that you're going to have to identify on the exam, is which particular methods require the use of certificates on both sides, which require use of server-side certificates, and which ones don't require certificates at all. If you recall, EAP Fast doesn't need any certificates at all, whereas PEEP and EAP TLS, EAP TLS and PEEP TLS require mutual certificates on each side, and PEEP and EAP GTC, we only require server-side certificates, and then we can verify the client some other way. If some sort of certificate-based authentication is used, the client needs to verify the server's certificate, make sure it's valid first. In PEEP, EAP GTC, EAP TLS, PEEP TLS, EAP Fast, etc., the ISE server acts as the server side, and it presents its identity certificate, which is usually signed by a third party, to the client itself. This identity certificate could be self-signed, but you're going to have an issue with the clients coming up with some sort of message indicating that the client is, or the certificate is not trusted, or the certificate is not verifiable. So a lot of times people will go ahead and go through the process of getting that certificate digitally signed. We deploy the certificates using the certificate authority architecture to be able to get those certificates signed, and then install those certificates on the ISE platform to be able to so that they can be presented to the clients as needed. The clients themselves, we don't really have a very scalable way to verify self-signed certificates. So in most cases, we prefer to have that identity certificate of the ISE platform digitally signed by a third party, so that we don't have to go through and manage that process with the self-signed certificates. All right. So the first thing that's going to happen, and what you're looking at in this, so here is the digital certificate that's being presented from the ISE platform to the client itself. Now, the client has the CA root certificate installed, and what it's doing is It's trying to verify the identity of the certificate based on this digital signature right here. Now, what essentially the certificate itself is not encrypted, right? It's sent essentially in plain text as a file that you can actually open up in an ASCII editor, or you can actually open up in a certificate editing application. But what the CA does is the CA who issues this certificate based on, or actually signs the certificate, it doesn't necessarily issue the certificate, but it digitally signs the certificate, is it uses some sort of hashing process, takes all the data that's incorporated into the certificate itself, and it uses the CA's private key to hash that data into a hashing, runs it through a hashing algorithm. Usually it's going to be SHA, and then there's obviously various forms of SHA that are available. All right, so now what happens is we've got this signature, which is basically the hash that goes into this field. That certificate gets sent to the client. We've identified the signer inside the certificate. The identity of the signer is listed inside the certificate, and the client, it has a root certificate, which happens to be the public certificate of the signer, installed in its browser or installed in the operating system, whatever it might be. We can verify this hash that was created as part of the signature by decrypting the data and decrypting the hash essentially, and comparing the results. And basically, if the information is the same, this thumbprint or this fingerprint is verifiable, then we know that the certificate is valid and it's been signed by a third party. That makes sense. Okay, so this process is not unique to Cisco ISE. It's not unique to this overall communication process. It's obviously part of TLS, and TLS is widely used in a lot of different areas. All right. So the client is validating the server's authenticity by verifying the server certificate, and then also verifying the signature on that certificate itself using the public key of the CA and so on. All right. There is a second validation that takes place as well. In the second step, the client examines the data arriving from the server. The data which is being provided by the ISE platform is also signed, and that signature is appended to the payload of that information. The signature is hashed by ISE, and then the hash gets encrypted using the ISE server's private key. The client then can extract the ISE public key from the already verified ISE certificate, and it uses that public key to decrypt the ISE signature. We compare the two hashes, and if the hashes are the same, then we verify the authenticity of the payload information as well. So not only are we identifying the ISE platform, but we're using this process to also verify whether or not the data or the payloads that are being sent back and forth between the ISE server and the client are valid, right? We don't typically use this for bulk encryption. We use this for a couple of different, we use this in a couple of different ways, but not for bulk encryption. Typically, we're using something like AES or something a little bit more efficient for doing our bulk encryption between the two endpoints. Okay. So how do we enroll? Well, it's a basic process. We'll actually see this. You guys are going to be doing this as part of one of the lab exercises that you'll be doing a little bit later on. But it's a pretty basic process. There's about 5 steps that are involved here. Number 1, we need to import the CA certificate, whichever one is that we're going to be using. And we could actually import several different CA certificates if there are other, multiple CAs that we're going to be working with. But we need to get the CA certificate from the CA, and then we're going to install that on our ISE platform. Then we need to generate a certificate signing request. Contrary to popular belief, we don't ask the CA to generate a certificate for us and then sign it. We generate our own certificate, and then we simply send that certificate up to the CA to have it digitally signed. So this generating a Cisco, I mean a CSR, a certificate signing request, allows us to take our self-generated certificate and send it to the CA for signing. Export the CSR to the CA, issue and return the identity certificate that's performed on the CA itself. So they're going to issue and sign and then return the certificate, and then we need to bind that or install that certificate based on the pending CSR that we had in the system itself. Pretty straightforward process, not too complicated. There isn't really a whole lot to this process. We will see essentially the areas that we go under administration and system and certificates, and then we can specify different components, you know, to be able to import certificates as well as get our certificates digitally signed. So let's take a look at what that process looks like and kind of go through the steps here. All right. Number one, importing the root certificate. We're going to go under certificates and go to our certificate store, and then we can identify the certificate file and then import or add and import that certificate. In this particular case, it could be in kind of the newer interface, by the way. It looks very similar. You're going to go to administration, you're going to go to system, and then you're going to go to the certificates menu, and actually you're going to identify local certificates, and we're going to import those certificates as well. Very straightforward process, not all that complicated. Just go to administration, system, certificates, certificate store, and then import the certificate. There are self-signed certificates that are provisioned during the ISE installation process. This certificate is going to be used by default unless you go through the whole process of generating a certificate and having it digitally signed by a third party. We could set up a multi-mode deployment without a CA. We could use the self-signed certificates that are installed on each of the ISE nodes during the installation process, and then we would only need to copy those self-signed certificates onto the other nodes in our environment. This does increase your responsibility as an administrator because you're going to have to, as you add each node or you change nodes, you're going to have to manage those certificates. You know, one of the key components is obviously enrolling or obtaining the root CA certificate from the CA itself. It depends on how you decide to get that. Will depend on the root that you're working with. Usually you can get it from an HTTP process or an FTP process. And then you also have to verify the root certificate authenticity over an out-of-band channel unless you inherently trust that particular root CA. The CA root certificate gets automatically enabled for things like securing LDAP sessions to an external LDAP server. And in a lot of cases, you're going to use certificates to authenticate clients as well. So you're going to need the corresponding root CA for those certificates that are being presented by the clients to be able to authenticate the clients effectively. Okay. Now, if we want to generate a CSR, one of the options that we have is to generate a, go through the process of generating a certificate signing request. Every ISE administrator account is assigned basically one or more different administrative roles. To perform this particular operation that we're seeing here, we have to be able to have, number one, the super admin role or a system admin role assigned to us. So that's something that's necessary in order for us to be able to generate the CSR. So we're going to go to administration, we're going to go to system, and then we're going to go to certificates. And then from that particular screen, we're going to click on the local certificates menu, and then we're going to click add, and then we're going to click generate a certificate signing request. We put in the subject name, the required key length, etc. The certificate subnet, a subject should be maybe a distinguished name identifying the entity that's going to be associated to the certificate, something that you might be able to identify. And it also has to include a common name value. It's important to note, though, if your purpose is to use the certificate generated from this CSR for, say, for example, HTTPS communication for management interface, you need to make sure that the CN value in the certificate subject is the fully qualified domain name of the node itself. Very important. Otherwise, you're not going to be able to select the management interface when you're binding this generated certificate. So that's something that I've run into before. All right. We then click Submit, and a CSR and the private keys are generated and stored in the Cisco ISE platform. We never send the private key to the CA. And we can view that CSR in the certificate signing request page. We can also export the CSR, send it to the CA to obtain that, that digital certificate. All right, pretty basic process, fairly straightforward. And as I mentioned, as far as the CA goes, or the certificate goes, it has to at least contain a common name or a fully qualified domain name. You can also specify SANs, which allow essentially the mapping of multiple subject names to the same private / public key pair. I recommend using a key space of 4096, although the NIST standard or the NIST guideline right now is about 2048 bits. The key length does affect the overall strength of the signature. Anything over 2048 is not going to be... If you have a key space of 2048 bits or more, that's not going to allow Cisco IP phones to authenticate, so keep that in mind, because the maximum key space on a Cisco phone is 2048 bits. Although 2048 bits is generally recommended. So we have a couple of different hashing algorithms that can be used here as well, SHA-1 and SHA-256. I do, of course, recommend that you use SHA-256. Once you've submitted your CSR to the CA and you obtain that identity certificate from the CA, you then need to go and install that CA approved and CA signed identity certificate on ISE. So we go to Administration, System, Certificates, Local Certificates, click Add, and then click Bind the CA certificate. From that Bind CA certificate menu, we can then associate the CA signed certificate with the pending CSR. Okay, it's actually a pretty straightforward process, very easy to do. The verification process is even relatively simple these days. Usually you just need to have some sort of email account or something that allows you to click and verify the authenticity of a certificate. Andy, did you guys, I mean, you guys obviously went through this process. What did your CA require from you guys to be able to verify the identity of their the ISE node? Was it just an email that you had to click on?
No, well, I mean, the RCA, because we used GoDaddy.
Okay.
So we just created a certificate off of the CSR, and it didn't even, well, you know, we already proved, because we have so many certificates anyway, that we already own the domain.
Oh, okay.
So, yeah, so it didn't require anything extra.
Yeah, I know when we just recently added a certificate to our website, and in the past, I know I've done certificates in the past where the CA will actually call you, or somebody will contact you, they'll send you emails, they'll go through different verification steps, but now it's pretty much all electronic now. The only thing I got was an email saying, click here to verify your authenticity, and the certificate was issued. So I imagine that's probably a similar process, although you guys didn't have to do it because you were already verified from previous certificates. But
right, we have a campus PKI with, I think is with Komodo.
oh, okay. So you guys are acting kind of as your own CA, or?
Well, we submit them to them, but we have a campus account that we use.
Oh, okay. Which they recognize as trusted. Yeah.
Right.
All right, well, step number 5 is binding the certificate to the pending CSR. When you're going to go ahead and process this binding operation, you have to go to the identity certificate file itself. You can enable the use of this identity certificate for certificate extensions that validate certain certificate attributes using an external user database. You can enable the use of a wildcard certificate that can apply to all kinds of host names or a subdomain or an entire domain. Or we can enable the certificate for use for EAP, which is pretty typical, or enable the identity certificate for HTTPS-based administration. It doesn't have to be limited to just one function. You can use the certificate for multiple functions as well, and that's pretty common. Then finally, you click Submit to install the identity certificate on the system. All the application services restart, and then you'll have to log back in, of course. All right. To verify the enrollment, it's pretty straightforward. You just simply go in. Oops, sorry, that's the wrong slide. Verify enrollment by going to Administration, Systems, Certificates, and Certificate Store. Or you can actually just connect to the platform itself and verify the certificate itself, or go through some sort of authentication process to see the certificate as well. Since the server authentication is always performed before client authentication, the supplicants have to successfully validate the ISE certificate before you can see any access attempts through the ISE GUI. So if there is an issue with the certificate, you would notice that as part of the initial process or the initial communication process from the supplicants themselves. All right. So that concludes that lesson. We talked about how ISE relies on the public key infrastructure to provide security for client sessions, HTTPS management, TLS protection, communication within the Cisco ISE deployment, even secure LDAP integrations, how we obtain those certificates, how we install the CA certificates or the root certificates, how we issue a certificate signing request, and then based on the response from the CA, how we install that certificate and then apply that certificate to different processes that might be necessary that would utilize that particular certificate itself. All right. So that concludes that lesson. In the next lesson, we're going to get into Cisco ISE Authentication, where we're going to talk about actually really the meat of what we're trying to accomplish, right? That initial authentication of endpoints. How do we set up an authentication policy? What is a rules-based authentication policy? How do we configure authentication conditions? How do we tune or create these compound conditions, and so on? So we'll talk about all of the components and the necessary pieces that are required to perform authentication within the ISE platform. See you in the next video.